we are starting now. Okay, so we are on, oh, perfect. I'm gonna write on a blackboard with a black marker. It's not gonna work. Okay, so we are on chapter 3, finally. So we're actually moving pretty quick, which is titled Interactions and Implications. So what we're going to do right now, hopefully today, we'll have a better explanation of exactly what temperature is and how it relates to entropy, which we had just previously described. Are we recording, Jason? Yes, we are recording. Thank you for asking. Always ask, even if I say I am, because chances are that I said I was going to and then didn't click it. Yes, I'm recording. Okay, so yeah, we had been previously talking about the second law of thermodynamics. But just realize though it's not actually a strict law, it's something that we're gonna just call a law because it approximately holds to a great degree of precision. So whenever we say the second law, just realize that the phrasing of law is kind of loose in a sense. So yeah, we're gonna figure out how S relates to things like the pressure, the temperature, and the number of particles. We want to know like what kind of function that is in general. So first of all, what we're going to start off with is the temperature. Okay. Well, so what does the second law tell us? It tells us that if we have two objects and they are in thermal equilibrium, then their entropy is at a max, right? So two objects in thermal equilibrium. And thermal equilibrium just means that the energy is distributed evenly across them. So we talked about how at this point, the entropy function is maxed. Okay, and also previously we had said that, like on the very first day of class, we had said that the definition of temperature that we're going to work with is basically that it is the thing that is the same when two things are in thermal equilibrium. So just looking at this, it might seem right off the bat that maybe entropy is going to have something to do with temperature. So what we're going to try to do is try to find exactly what that relationship is. So to do that, let's consider two Einstein solids. Just an interacting system of Einstein solids like we've considered over and over. Let us take Na to have 300 oscillators, and B to have 200 oscillators, and the number of total energy units to be 100. Okay, so if we were to work everything out, we would show that this model reaches equilibrium, which I'll just write as that, at QA equal to 60. And the reason it's not 50 here, the reason it's not just half, is because now these systems are uneven, right? So now distributing the energy throughout both of them doesn't just mean that QA is half of the total. It means that it's proportional to whatever the number of oscillators in each of them is. So that's why it's 60 in this case. So it reaches equilibrium at this point where S is max. So an equivalent way of saying this is that the entropy function, S total, taking the derivative of it with respect to QA, and then evaluating that at equilibrium, should be 0, right? That's just telling us that our entropy function is at an extremum. So we can also write this. Wait. Yeah. As del U A at equilibrium equals 0. So these are the same things, since the number of energy units is just proportional to the actual units of energy itself. So no fancy business going on there, at least. So now we just have to remember that entropy is additive. So if we have two systems, one with entropy A, one with entropy B, the way you find the total is just by adding them together. So we can take that expression that we just had, the del S total over del UA equals 0, at equilibrium. I'll just write E here for equilibrium. So we can rewrite this, expanding it out, del SA, del QA, evaluated at equilibrium, plus del SB, del, oh, sorry. I'm using U's, aren't I? UB. That should equal 0. Okay. So we also know that the total energy has to be distributed throughout the system. So if you take whatever's in A, whatever's in B, and you sum them up, that should be the total. So what we can do is we can take the differential of this. So since U is a constant, taking D of U total will just give us 0. So if I take the differential of this whole expression, I'll have a 0 on the left-hand side. I'll have a DUA plus DUB. And I think I actually made a mistake up here. This should be, I never actually changed from UA to UB just yet. That's what we're doing right now. So this line up here was just breaking up S total into SA and SB. The derivatives should still be with respect to A. So if we want to change this derivative and make it into a derivative with respect to B, that's what we're doing right now. So we can show that the differentials should just be opposite each other, which makes sense. As you put something into one, the other one has to lose. So if we know this relationship between the two differentials, then we can rewrite this expression right here. So now it should just become this. So just put a minus sign on it, and then now its derivative with respect to B at equilibrium should be equal to 0. Okay. So you could also just write this So this is a statement that holds at equilibrium, that the slopes of the respective entropy functions should be the same when you take the derivative with respect to their respective energies. So specifically now, we can point to this slope of the energy function is the thing that is the same for both systems when they're at equilibrium. So previously we were saying that temperature is the thing that is the same. So now we might have some kind of guess, like, well, obviously, like mathematically, this is actually the thing that's the same. So is there some way we can relate this to temperature? And just to get a little bit further into this in our analogy between this slope and temperature, I probably won't do a great job of reproducing exactly what the plot looks like in the book. It looks something like this. So if you were to plot QA, sorry, the total entropy function S versus QA. So for system A, it would look something like this, something like that. And system B would look something like this. And then the total just looks something like this. And so basically this point right here, maybe everything won't match up perfectly, but just understand what I'm saying. So this point right here is where our total entropy is maximized, right? Because right here the slope is approximately just 0. And if we look at some point on each A and B, some way away from equilibrium, so let's take like this point right here. So on system A, its slope looks like something like that. And if we go at the same point on B, its slope looks something like that. So we see that the slope of the system A entropy is bigger than the slope of system B entropy. So, well, what does that mean? It means that this thing, if you add energy to it, since its slope is bigger, adding energy will increase the entropy a significant amount more than it will be for system B, right? Since the slope is bigger. So write it as such. So slope of SA, we'll call that point QA equals 12. We're just going to take the absolute value as well, because one's positive and one's negative, obviously. So what I'm saying is that if we pass energy from B to A, then SA gains more entropy than SB loses. Since SB's slope is smaller and SA's slope is bigger, overall the entropy goes up. So overall, the total entropy increases. Does that make sense to everybody? Okay, hopefully. So the second law, it says that entropy will flow from low-sloped S system to a high-sloped S system until they come to an identical slope. That's just what we were saying just before. So basically, del UA is greater than del SB del UB. So this is just what we were saying before if we're looking at that point out of equilibrium. So if you had to assign to this one and this one, either one is hotter or colder, which one would you say is hotter? Which one would you say is colder? Any ideas? So think back to what we were talking about with temperature earlier on. So we talked about temperature as a sense of a system's willingness to give up energy, right? So here, left hotter. Left is which? This one's hotter? Not quite. So saying B is hotter. Yes, yeah. Carter and Carmon said the correct thing. I see, yeah, so you think slope bigger must mean hotter, but what the slope means here is that it's more willing to accept energy, right? It's more willing to accept the energy. So in general here, what's going to happen is entropy is going to flow from, or energy is going to flow from system B to system A, because that increases the entropy. Well, if energy is flowing from B to A, then you must probably think that this is probably going to be hotter, since energy is flowing from there to here, and this one should be colder. So that might be right. We're getting closer to relating this exactly to a temperature. So now we can ask ourselves, what are the dimensions of del S over del U? Well, what do we know the units for entropy to be? Anybody remember? Should be joules over Kelvin. And the units for energy, of course, are joules. So then this must have units of 1 over Kelvin. So look at that. We're really getting somewhere now. So we know that this thing relates to temperature in some way or another, and we know it has units of 1 over temperature, or 1 over Kelvin. So at this point in time, we might take a shot in the dark and say, hey, well, if we take the units of the inverse of this, so if we take del S, del U, we invert it, well, we know that this has units of Kelvin, so is this temperature? So for the moment, what we're going to do is we're just going to assume that that's correct, and we're going to work with it and prove to ourselves that it holds up with our reasoning for the way temperature should behave mathematically. So here, the subscript n and v is just saying that we're holding n and v constant, which we're doing this whole time. In the Einstein solid that we're considering at this point in time, the only thing that can flow is energy. So both the number of particles and the volume of the system is held constant. Eventually what we'll do is we'll convince ourselves that temperature is the correct relation here, and then we'll allow our system to now exchange the number of particles, we'll allow it to exchange the volume, and we'll show how these varying and coming to equilibrium correspond to different quantities like temperature. And specifically, it'll be like the chemical potential for N, and it'll be like the pressure for V. So this is the definition of temperature that we're going to take now. This is our evolved definition. So let's take that and work with it. And in the book, Schroeder goes through this little section he calls a silly analogy, where he relates entropy and whatnot to greedy and miserly people and whatnot. I didn't really like that, so I'm not going to talk about it at all. You can read it if you want. It seemed like it was more confusing than anything. So I would just think of entropy, think of temperature in the way that we just described right now. So what we can do now is if we know what the entropy function is as a function of U, the energy of the system, well, then we can calculate its temperature. That's just what that previous relationship was telling us, right? So why don't we take a system for which we know the entropy is a function of the energy and calculate this and just see what happens. So let's go back to our old friend, which we'll just keep coming back to, an Einstein solid. And we'll take it in the thermodynamic limit, which is just saying that the Einstein solid is hot. So the number of energy units it has is much bigger than the number of oscillators it has. So we showed, or you showed, that in this limit, we had the multiplicity function looked something like this. It looked like E times Q for N to the N. That was for this limit. So now if we have entropy defined as N times K entropy is just K times ln of the multiplicity function, then for an Einstein solid in this limit, it just becomes the following. So it's going to be ln Q over N plus 1. Okay, so if we break this up a little bit, a couple steps, really only one step, ln of U, just using we're going to relate U and Q via this relationship right here. So if we use that, plug it in, we can rewrite this as the following. And so since we're trying to relate the temperature to the entropy, and we only care about the derivative with respect to the energy, we're only going to concern ourselves with this term right here. These other two terms are just going to contribute 0 to the derivative, right? So at this point, maybe just ask yourself, what would you expect for this result? What would you expect T to be for an Einstein solid? Do you have any notion for something that you think it might replicate? Did we have a relationship previously that related temperature to energy that you could use for an Einstein solid? Anybody? Think way, way back to a week ago. 2 weeks ago. Was there a theorem that we cited to not heat capacity, not the ideal gas law? Although, I mean, it'll align with those things for sure. So it's the equipartition theorem. Yeah. There's Austin with it. Nice. So we know, remember like our vision for what an Einstein solid is, right? It's like just a bunch of particles sitting together with some like spring type interaction between all of them. And this could be in many dimensions or whatever. And so previously we had talked about how many degrees of freedom you would have for spring degrees of freedom. So you would expect there are 2 degrees of freedom for every single spring, right? So that would just mean that F equals 2 in the equipartition result. So we might expect this should just confirm that U is equal to N times K times T. So let's just make sure that's the case. Question. Yeah. Who's got a question? After the end. This epsilon, it is just something with the units of energy that converts between like the dimensionless thing Q and the thing that has units of energy U. It's just that we have something with the right units. So our definition of temperature that we just wrote before is del S del U, the -1. And just always remember that we're taking this with respect to N and V constant. So if we write this, we would get N times K, and then we'll only have to take the derivative with respect to U of the log part, right? Because the rest of the terms in here don't involve the energy, so they'll just vanish. So this will be N times K over U to the inverse. So this is just going to be U over N times K, not K times K, N times K. So if we were to rewrite this, what would we get? It's our good old friend, the equipetition result, right? So it just confirms exactly what we got over here. So that's good. That means that the definition of temperature that we're using right now at least aligns with what we had taken to use in terms of temperature previously. So this is a nice thing. This is the kind of thing that you want to prove to yourself when you're just coming up with definitions for thermodynamic variables willy-nilly like this. Okay, so does everybody agree with this so far? Just confirms the equipetition result? Okay, cool. Now let's just do it again. Let's do the same kind of thing again. So now let's take a monatomic ideal gas. So what do we think it should be in this case? What do we think U should be? What's our guess? Well, not a guess, but for the equipetition result, right, we had it should be N times F over 2 times KT, right? And how many degrees of freedom are there for a monatomic gas? Thoughts? Monatomic, remember, just means that it's like a point particle just zipping around. It only has kinetic energy. And so for in 3 dimensions, F should just be 3, right? It's just got 3 degrees of kinetic energy. So we should expect that this is going to be 3 halves N times K times T. So now let's go back to last chapter and pull out this ugly formula for the entropy that we had. So we showed that the entropy should look like this, B over N, 4 pi mu or 3n h squared, 3 halves plus 5 halves. So this was the result for the entropy that we showed in the previous chapter. Okay, so this gives us S as a function of U. So now we just want to purely extract that dependence on U, take the derivative with respect to U, and show, hopefully, that it confirms this result right here. So if we were to break this down, we would show that S as a function of U just looks like N times K ln of U to the 3 halves, plus a bunch of other stuff that we don't care about, right? So the only part that we care about is this log of U to the 3 halves. The rest of it doesn't depend on U whatsoever. So when we take the derivative, it'll just go away. So we're going to absorb it into these ellipses right here. So let's take our definition for temperature once again. So we said it was del S, del U, -1 with N and V constant. So if we take the derivative now, we would just get that this is 3 halves N times K over U inverse. And so what do we have? We just have that U is equal to 3 halves NKT. Look at that. So it looks like we're on a roll right now. So it looks like we have a definition for temperature that lines up with everything that we did for previous systems. So this is good. Okay, are there any questions about that? Just a straightforward application of stuff that we talked about last semester. So now I think what we're going to get to, I guess we're not quite to that. Let's move over here. So we're going to talk about the relationship between entropy and heat. So at this point, if you're given multiplicity as a function of u, or you can calculate it in some way, then you can get the entropy as a function of u, just because you just take k, Boltzmann's constant, times log of the multiplicity, get the entropy. Then you could get the temperature. So if we were able to calculate that, then we can go to there, then we go to there, boom, you got the temperature. Cool. So what did I want to say here? Oh yeah, I guess mainly that sometimes for like real systems, this multiplicity here isn't actually going to be super easy to calculate. So it won't always be super straightforward to start at this point and move to the temperature that way. So another thing we could do is we can consider the heat capacity. So let's compare. Let's compare our results for using heat capacity at constant volume. Draw an arrow there, because that's the thing we're comparing to. So when we defined heat capacity at constant volume, it was defined as the following: del U, del T at constant number of particles and volume. So using the Einstein solid in the thermodynamic limit, then we can show that CV del T of n times k times T. And that is just n times k. Now, so it's just constant with respect to temperature. So if we also take monatomic gas, then in that case, CV is just going to be 3/2 n times k. So at least in both of these cases, if you look at the heat capacity at constant volume, using what we had just calculated and then calculating the heat capacity, you just find that heat capacity of these two different things is constant with respect to temperature. Does anybody think this is a realistic result? That things just continue to change their heat as, or continue to change their temperature as heat is shoved into them? Well, it's not in general. So in general, you don't just have these constant expressions right here. In general, they are a function of temperature. So yeah. So yeah, in reality, it's really hard to get this function omega right here. So what we're going to do is eventually in chapter 6, we're going to introduce a different route to get to what u of t looks like. But for now, this is what we're kind of stuck with. So if we can't write a nice mathematical expression for what the multiplicity is, we can still take the specific heat at constant volume. We can use that to get u as a function of t. And then we could use that to get to the entropy. So let's look at our definition. So we said that temperature is defined as the following. T. And here, hold up. So I'm just going to write this using total derivatives now, just to get it into a form that we're familiar with. But in general, S is not just a function solely of the energy. But since we're holding U and V constant, or sorry, N and V constant here, this is safe to write. So using this, then, we could write that ds, the differential of S, is just equal to du over t. Well, there's no work being done at this point in time, so we could just write this as the heat over the temperature. So do you think that this is going to work? Do you think that the change in entropy will be able to be written as the heat over the temperature if the temperature is changing? What would we do in this case when the temperature is actually changing? Any thoughts? So I mean, you could calculate the change in entropy using the heat over the temperature. As long as you add heat to whatever this thing is, the temperature doesn't actually change at all. But if it is changing, obviously you're going to need to use the specific heat in some way or another. And so the way you're going to do that is what we'll show. So let's take CV. We had that defined as del U, del T, and V held constant. We can rewrite that as Q over dt. So then you could write CV dt equals Q. And so then if you actually had your temperature changing, you could plug in this expression for the heat into here, and then you would just have to integrate with respect to the temperature. So in that case, you could take ds CV dt all over t, and then to actually find the change, you would just integrate this expression. So yeah, let's integrate it. So if we considered stuff like we were just talking about before when we calculated the specific heat at constant volume, in those cases at least, CV as a function of T is just a constant. So it's not a function of CV or of T. So in that case, then you could just write that the change in entropy is going to be CV, and then you'd integrate from Ti to Tf, dt over T, and we all know how to integrate that. It's just going to be the log of Tf over Ti. So that's going to be the change in entropy if the specific heat doesn't depend on the temperature and you're changing the temperature in some way or another. So let's take this expression and just calculate it for an everyday object. So for example, like what is delta S for, what did I do? Heating cup of coffee, which we'll say is like 200 grams. And we'll heat it from Ti equals 20 degrees Celsius to something that's nice and hot, that'll warm me up in the morning, 100 degrees Celsius. So coffee is mostly just water. So its specific heat's going to be this. And we'll just take that it's roughly constant over this range of temperatures anyway. So in this case, we can calculate what the change in entropy is, just using what we wrote before. So it's going to be 840 joules per Kelvin, and then times the log of 373 Kelvin, all over 273 Kelvin. So make sure to always change from Celsius to Kelvin whenever you're putting anything in thermodynamic expressions. We talked about that really earlier on, but it's especially important here as well. You always need to be working with this absolute scale when you're calculating these values, otherwise you'll get nonsense answers. So this, if we plug it in, we would get that our change in entropy is 200 joules per Kelvin. So this is just displaying what a typical change in entropy is for when you're literally just adding heat to a system. So using the fact that S is defined as K log omega, and inverting is what that says, to find delta omega, we could get that the change in the number of microstates for this addition of heat to the system right here is something that looks like e to the 1.5 times 10 to the 25. So this is actually kind of interesting. I mean, for just heating a small cup of coffee, 200 grams, from 200 Celsius to 100 Celsius, the change in the number of accessible microstates is e to the 1.5 times 10 to the 25. That's an absolutely huge number. So your conversion from C to Kelvin might be wrong. Yeah, did I do something wrong here? Oh yeah, you're absolutely right. Yeah. Yeah, I meant to just take that you're going to go from something that's at like roughly room temperature, but a little bit colder, to just 100 Kelvin higher. Obviously, this is not correct because the change from the two scales have the exact same increment. They're just offset by 273 degrees Kelvin. So that's not correct. Just take that I gave you this. Thank you for that. Sometimes I write the wrong thing. Okay, so yeah, this is just displaying. Oh yeah, safe. What's your question? Mm-hmm. Right, right. Yeah, no, that's actually a really good question. In order to actually calculate the entropy at a specific point in time, you would need to have some way of calculating the microstates at that specific uh, point in time and state. Okay. So I've got a little note here. So note that delta S equals CV ln of TF TI. It can't possibly hold as you take the initial temperature and send it to 0, since this is going to diverge. Um, so basically, the way that you actually overcome this weird like divergence that you see here, if like you take the temperature and take it to absolute 0, is that in reality, when we're talking about real substances, this specific heat, it will not be constant over that entire range. And in general, if you were to integrate from like some positive temperature to absolute 0, this CV will be such that it takes the initial or the bottom entropy to be 0. So just note that this is only going to be true when CV is constant, that you can observe weird results when you take things to be constant that aren't actually constant in real life. So let's say that you did know what CV was down to t equals 0. So you did know CV. So in that case, you could write the change in entropy. So this is at 0. And then you'd be able to integrate 0 to TF, CV over T dt. But this bottom state right here, it should be 1, since the lowest energy state is completely unique, right? So when we take it down to 0 Kelvin, there's a single microstate corresponding to that. So this should a unique state. But so what happens in practice is that, I'm not sure there's really a whole lot I want to write here. So maybe I'll just go back. So in practice, this should just be 0 because S of a single microstate, so S is just K times ln of omega. If omega is 1, there's a single microstate, then the log is just going to be 0, right? So this should, in practice, shouldn't theory be 0. But something to note is that in reality, it's very, very difficult to actually ever observe this bottom state. So a good example that's listed in the book is the example of ice. So theoretically, when you've got this collection of molecules, so let's say you start off with some box of water, and what the water looks like, it's got a bunch of H2O molecules, and they're flying all over the place in different directions and whatnot. And then you take that and you freeze it. Well, if you don't freeze it very, very, very carefully, these are just going to freeze into place approximately. So they'll still look like they had some random direction when they froze, so they'll have some random orientation. It's hard to draw that exactly, but it won't be like a nice ordered thing. So in general, the actual bottom state should be something that is very orderly, something that looks perfectly like this. But in practice, as you do this freezing process, you slowly do it, they're going to freeze into spots that don't actually correspond to this bottom entropy right here. So the difference between this state right here that you froze into and now they're all locked into place and the actual bottom entropy state right here is just what's called and referred to as residual entropy. So that's not really something we're going to make a whole lot of use of, but it's just something good to know for experimental uses. Okay, so I think that's actually all I wanted to cover today. We actually made it through a good part of chapter 3 so far. So yeah, we'll talk more about it on Friday. I'm sure we'll spend a decent amount of time on Friday talking about what went on with the exam. But then after that, we'll start going through the rest of chapter 3. We'll talk about extending a lot of these results from simply allowing energy to exchange between two systems to now allowing volume to exchange and the number of particles to exchange, and showing how those variations now correspond to different thermodynamic properties like the pressure and the chemical potential. So if you have any questions about like the practice exam or anything, feel free to hop in my office hours after I close this. Otherwise, are there any questions about anything we just talked about? I don't see anything.